Today we're going to talk about the sparse vector technique. Let's start first of all with a setting that we've seen a few times before. Let's suppose we're answering a set of queries. So imagine we have a set of k sensitivity 1 queries that come to us one at a time. So there's functions f1, f2, ... all the way up to fk, and they come into us in an online fashion. What do I mean by online? That means we have a set of time steps, and during each time step, a single function comes to us, and we have to answer that function and then move on to the next one. So, yeah, imagine at time t, you have like a certain query function comes to you, ft arrives, and you have to answer what the value of this on the data set privately. We need an answer to ft of d privately. Now, we know how to do this pretty well, in the sense, first of all, like the natural algorithm for doing this would just be to add Laplace noise. So let's suppose our overall goal was epsilon dp. And also for most of this lecture, we're going to focus on the case where these are all sensitivity 1. So in particular, we've looked many times at the case where things are sort of normalized, but here we're going to unnormalize it, where, you know, this is sort of a count query rather than, things are sort of counting rather than being normalized. So suppose we want epsilon dp overall. Well, all we have to do is answer very simply. We just have to output at each time step fi on the dataset d. Let's say ft just because that's the notation we've used, plus some Laplace noise, which is of magnitude k over epsilon. And why is that? Well, you can just see that there's k queries overall, and if we add Laplace k over epsilon noise to each one, then by basic composition, the overall thing will be epsilon dp. If we wanted to do approximate differential privacy, well, it's very similar actually. We can essentially do the same thing, just using, say, like, for example, we're not going to worry about too much about the other lower order terms, but roughly you can do something like this. You can add Laplace square root k over epsilon noise, and if you used advanced composition, then this will give you the appropriate accuracy or privacy bound. So what do we want to say here? We can see that the error induced on each query is going to be order k over epsilon for this, and square root k over epsilon here. The point is that both of these errors introduced into the answers for our queries are polynomial in k. So this is not bad, you know, it's square root k, but it's still polynomial, which could be very bad, as sort of we discussed last lecture, if the number of queries we want to answer is very, very large. So instead, let's relax the problem a bit and let's solve a slightly easier question. Instead of trying to answer every query, we're instead going to try to answer the following question: which queries are large? Where there's a bit vague for now, but we'll get into it a bit more. There's a bit of hope here. For example, suppose we were given all the queries, like suppose I said we're going to be in the online setting where you have to answer things one by one, but let's suppose we were in the offline setting where you were given all of the queries before in advance. In this case, you could take your f1 and your fk, and what you could do is you could run the exponential mechanism. So in this case, what you could do is essentially find, what do we do? Our set of objects would be, you know, let's set it up as the way we have usually. Our data set is, you know, the data set D. The set of objects are just going to be these functions here. And the score function for each thing will just be the value. So the score will be equal to f of I on the dataset D. So now what would we get if we use the exponential mechanism? if we use the exponential mechanism, we would get something which has approximately the largest possible value of any of them in the data set, or sorry, in the set of objects. So it'll return it'll return the largest query, really, is the point, approximately. So now this will give us the largest one, and then if we want to find the second largest one, then we could just run it again, and so on. So roughly, what I'm saying is we could find, if there were C large ones which we were trying to find, we can find C large queries, and the cost of doing this would be C log K over epsilon. Where did I get this from? Well, essentially, I'm just saying run it iteratively. So, sorry, let's just ignore the C for now. If the C wasn't here, then this would be the cost of doing the exponential mechanism once. We kind of learned that the cost is log of the set number of objects times the sensitivity divided by epsilon, so log K over epsilon. But the way you would do this if you wanted to find C large queries is to run it iteratively on the set. And if you want to do it C times in a row, then by basic composition, you would need to rescale the value of epsilon by a factor of C. So overall, the cost is C log K over epsilon. Or you could do, C square root C times log K over epsilon if you were okay with approx dp. This is, just a square root factor instead of a linear factor. Okay, so that's great, but the bad part here is that we were in the offline setting where we were given everything beforehand. The question is, can we instead do this in an online setting like we wanted? And if we want to do this in an online setting, then we'll do this we'll use what's known as the sparse vector technique, which we're going to introduce in today's lecture. So what we were doing here is trying to find C of the largest queries, which is, we left it a bit vague nonetheless, but we're not going to be able to find the C largest queries. For example, suppose if you were looking at the very first query, you can't tell just looking at it whether it's going to be one of the largest or not. So in the online setting, we're going to be trying to answer the following question: which queries are greater than some threshold? So there's some threshold T, and that's going to be kind of our goal, to return the queries which give a value on the data set. Specifically, which queries, what I mean by this is, which fi of D are greater than or equal to T. So yeah, that's what we're trying to answer. This is the threshold T is going to be publicly known, we assume. And yeah, that's sort of the setup for sparse vector. We're given a sequence of K sensitivity 1 queries, and the goal is to identify which ones are greater than T. The idea is I'll comment that we'll be able to answer this. We're going to have some specified C where we're trying to find the first C queries which are greater than the threshold T, and then the algorithm will halt. So let me just write that down. So the goal is output the first C such queries. All right, now the algorithm is actually going to be very, very simple. We'll see it as we progress, but it's notoriously hard to get the details precisely right. Even the version of the algorithm I'm going to present in today's lecture is slightly weaker than what you could want. There's some things which raise the accuracy a little bit, but we're not going to get into that. The point is that this is a very careful one where everything comes together in just the right way. And yeah, many people have got this wrong in the past, including in published papers. So the idea is we're just going to, at its core, it's a very simple idea. All we're going to do is run the Laplace mechanism for each individual query and only return the ones which are greater than some threshold. However, the tricky part is we're not going to use the threshold itself. We're not going to use the threshold that we're trying to figure out, T. Instead, what we're going to do is we're going to noise the threshold instead. Noise the threshold as well. So this is very interesting because like the effect of noising this threshold in the proof will allow us to privatize all but the last query, whereas noising the query itself will privatize the last query. So this is a bit vague right now. It might not be clear what I'm talking about, but I think it's the point I'm trying to get across here is that there's a very interesting use of how we noise this threshold, which is something qualitatively different to what we've seen before, because it sort of privatized many queries at once. Okay, so that's the kind of setup. We want to answer, we're given a sequence of, k queries in a row, which are all sensitivity 1, and the goal is to output the first c queries which are greater than some threshold t. So the idea is we're going to start with a very simple case. We're going to start with an algorithm which is just known as above threshold. The idea of the above threshold algorithm is it's going to focus on the case when c is equal to 1. It's going to try to output the first large query, and once it outputs the first large query, then it just halts. We're going to see later that this is essentially, we're going to just chain this together to create what's known as the sparse vector algorithm, where we, essentially every time we see a large query, then we start the algorithm again, and by composition, this will argue that the overall thing is private, as long as we rescale the epsilon parameters appropriately. So let's take a look at this algorithm here. You can see it, this is like the whole algorithm in these few lines. So what do? So it's given in the database, it's given in the sequence of queries, it's given in the public threshold, and it's given in this epsilon parameter, how to privatize, like how much privacy we want. The first thing we do, like I mentioned, is we actually noise the threshold t. So we have this threshold, but we're not going to compare with this threshold naively. We're actually going to create a privatized version of the threshold t hat. This is going to be for analysis purposes in the privacy proof later. So we're going to create some privatized threshold. What we do is for each query, as they come one by one, what we're going to do is privately get the answer of the query using the Laplace mechanism. So this generates some Laplace noise, adds it to the true query value, and then it compares it with this noise threshold. If it's greater than the noise threshold, what we're going to do is say, indeed, it's above threshold. So we output this symbol is called top. We output top, and then it halts. So it's kind of going to just go until it finds the first large query, and then stop. Otherwise, if it's below the threshold, then we output this other symbol called bot. And if in this case it doesn't halt, it just keeps going until it starts again, until it eventually gets to something which is above the threshold. So that's the algorithm. It's very simple. One thing that's nice to note here is that there's nothing in this algorithm which depends on the number of queries we receive k. Even this algorithm kind of states it as an infinite number of queries. And the cool thing is the fact that this will be useful in terms of getting the privacy guarantee. We can have an infinitely long stream and it'll still be private. What we are going to be hurt though is in terms of the accuracy guarantee. The more things in the stream, then the worse our accuracy gets, which is natural. But we'll revisit that later. The first thing we're going to do is talk about the privacy guarantee. The privacy guarantee is a little bit tricky, so pay attention. And what we can say is this is epsilon dp. So it's going to be pure differential privacy, purely differentially private. And like I said, the key thing that I want you to watch for as we go through this proof is the fact that this noising of the t hat is going to somehow privatize all of the queries which fall into this case, the ones which are below the threshold simultaneously. Which I think is kind of neat. So, okay, what we're going to do is, as usual, like we're going to fix, D and D prime, which are going to be neighboring databases. And we're going to let the outputs, the sequence of these A responses on the two algorithms be, this is sort of the output of D, and this is the output of D prime, A and A prime. These are going to be the outputs. And these are going to be the databases. So what are these outputs going to look like? Well, note that the way that the algorithm runs, it's going to output bot a bunch of times and then finally output top. So, we're going to let, it's going to be like, bot, bot, and then eventually top. So what we're going to do is we're going to let A be some particular output, some fixed output. These are sort of random outputs, but these are the outputs of the algorithm. But this is going to be some particular string, which we're going to call bot to the t-1 and top. So the idea is that this is going to be the specific string which corresponds to going saying no for the first t-1 times, and then on the tth time, then we output top and saying above threshold. So we're going to relate the probability that A equals A versus probability that A prime is equal to A, and we'll do this in the usual DP fashion. We want to show that this is less than or equal to e to the epsilon times this. But yeah, that's getting a bit ahead of ourselves. The idea is these are the two events we're going to try to relate the probabilities of. So the first thing, which is kind of not obvious here, why we're doing this, but the reason is because these values don't really actually matter that much. Essentially, we're going to fix the randomness in all of these random variables except for the last one. That is, we sort of noise the the values of the query for every single query we do. But the point is that the answers of the first t-1 are going to be truly irrelevant in the sense that we're going to get privacy elsewhere. This is going to be providing the privacy for them. So what we're going to do is we're actually going to fix these values like new 1 all the way through new of t-1. So we don't care what they are. We're just going to say that they are some values. Yeah. And all the probabilities, these probabilities here of the output being whatever, these are going to be computed only with respect to the value of, say, what t hat is, and with the value, the only randomness is going to be in t hat as well as new of t. These are just going to be fixed arbitrarily, and the rest of the proof still holds. So one thing we're going to find convenient is the following notation. We're going to say that g of d is essentially the maximum of the first t-1 queries. So not just the queries actually, but the privatized version of the queries. So this is going to be the max of the first t-1 queries after privatization. And the important thing to note that is because we fixed these values, these sort of noise parameters here, they are all fixed to be we're conditioning on them kind of for the rest of the proof. So therefore, this is deterministic. It doesn't depend, there's no randomness in this anymore because we've fixed the other realizations. So this is just some deterministic quantity. And now let's do the actual proof. So we're just going to sort of write things out and see what happens. So we're going to say the probability of A is equal to A, and I'll write this probability over t hat, comma v sub or new sub t, and I won't write these as the probabilities as the probability being over these anymore because it'll be implied for the rest of it. But yeah, so what is the probability that the algorithm outputs this? Well, let's see. It's going to be the probability, first of all, that t hat is greater than g of d, and that all the other ones are greater than the threshold. So why is this? You can see this because this is just saying that we need that the threshold is in fact greater than all of the previous queries, just so that it outputs bot for all of those. And the last one, we want it to actually be above the threshold and output top. So these are the two conditions that correspond to giving this output. This controls the first t-1, this controls the tth. Okay, well, this can be rewritten a slightly different way, just basically saying where this t hat lies. So this is g of d. This is less than or equal to t hat. This is less than or equal to f of t of d plus new of t. And yeah, that's the sort of condition we have. If this event happens over this probability, then we have the desired output. So let's just write this out. Remember, this is a probability, so we're just going to write it as follows. We're going to actually write it as an integral over the realizations of, we're going to write it as an integral over the realizations of these t hat and nu of t, and it'll be, and we'll use an indicator to sort of get a 1 for the times when this event happens, when this event happens, and 0 otherwise. Let's write this out in a little bit more detail. So these integrals from minus infinity to infinity. And the term that's inside is sort of this is going to be, I'm going to use a bit of an abusive notation here. This really means the PDF, but we'll just write it as the probability that's equal to something. So there, and this will be probably t hat that equals tau. And we're going to here use the, like I said, an indicator, which is 1 when this event holds. That is when, this is tau, and when this is in this range. That's like g of d, comma, ft of d plus nu of t. So yeah. And dv d tau. So you can see that this is just exactly equal to this because we're just integrating over the probabilities, and it takes 1 in the cases when this event happens and 0 elsewhere. Okay, at this point we've got it kind of convenient, but remember we want to switch it from trying to understand what happened on this data set D to what happened on this data set D prime, which is the sort of neighboring data set. So what we're going to do is we're going to perform a few substitutions in order to change from one to the other. So we're going to introduce the substitution that tau is equal to tau hat minus g of d prime plus g of d. This kind of accounts for the difference between, it sort of subtracts out one data set, it switches from one data set to the other and accounts for the difference. And similarly, we also let v equal v hat. This is a bit more complicated, but it's sort of doing the same type of thing. Just sort of factoring out, subtracting out one data set's contribution and adding in the other data set's contribution. So these are the two things that we're going to consider as substitutions. And what we're going to do is actually, for now, we're not going to touch these, but we're going to change this event from one to the other just by substituting in these values. So this part here, this is equal to the following. I'm just going to drop the limits of integration. They're the same, minus infinity, infinity. But we're going to say that probability that nu sub t is equal to v, probability that t hat is equal to tau, and then we switch these in. So this is just performing a substitution. So this becomes, we want the probability that, or the event rather, that tau hat minus g of d prime plus g of d is in this range. G of d is unchanged because we didn't do any substitution here. G of d. The next one does change a bit, so let me write that down on the next line actually, because this is a bit of a mouthful. Check the notes if you want to see this written out a little bit more carefully. But this becomes ft of d, and then this nu of t. Sorry, I guess this should be, or sorry, this is just going to be in v rather, because we're sort of substituting in the realization of these random variables. So here we just do the substitution that v is equal to v hat plus whatever. So this becomes plus v hat minus g d prime plus g of d minus ft of d plus ft of d prime, and close paren. Okay, so this is a little bit convenient because what we can do is this will allow us to cancel out this term here because the plus and minus the same thing. This is going to subtract from here. Sorry, this will shift this from g of d to g of d prime. These will cancel out. But the point is, if you do all these substitutions and sort of move terms over to the right-hand side, then we'll be given the following. We'll have these things are still unchanged. Probability of nu sub t equals v. All right, and these ones, after you do all the shifting stuff around and rearranging, you'll have the following. Tau hat is in, this subtracts and adds that, so that becomes g of d prime, comma, and then, like I said, these two cancel with this, and this becomes v hat plus f sub t of d prime. And this will be dv hat, be d tau hat. So now let's take a look at actually what we have here. This term right here is very similar to what we had beforehand, before we did the substitution, except the only difference is that we switched from d to d prime, which is great. The only thing that we have to change is now changing from these v to these new, we've changed sort of the integration here. So we have to also shift from this v and tau to these, to sort of recenter it, because we're really considering these variables tau hat and v hat. So what we can do at this point is by noticing the relationship between tau and tau hat, as well as the relationship between v and v hat. So what we're going to do is we're going to note the following. We're going to note that how far is tau from tau hat? Well, if the distance is less than or equal to g on d minus g on d prime. And this can be upper bounded here by 1. The reason is because these are sensitivity 1 queries, so therefore this gives an upper bound on their difference. Similarly, if you do the same set type of thing, you'll notice that the difference between these is less than 1 and the difference between these is less than 1, just similarly because they're sensitivity 1 queries. So therefore, we have that difference between v and v hat is less than or equal to 2. So with these two things in mind, the idea is that we're going to shift these from being centered around tau and v to being shifted around tau hat and v hat. And that's actually fairly easy to do just using the definition of the Laplace PDF. So this will be overall upper bounded by, double integral, and here we have an e to the epsilon, say expo epsilon over 2 times, now we've switched this from probability equal to v hat. And similarly for the other one, this will be now equal to probability that tau hat is equal to, t hat is equal to tau hat. And this will all be the same, so let's just copy paste that. Yeah, I mean, this will all be the same right here. Okay, so that tells us, what does this tell us now? Well, now this looks incredibly similar to what we had before, so we can just kind of move backwards in the sense that, I don't know, it shouldn't be too hard to pull this out. You just pull this out here and this here, and that'll give you an e to the epsilon. But the remaining terms, what you have here is, again, precisely what you had way back here. So this will let us rewrite this as times the probability that, first of all, t hat is greater than or equal to g of d prime, and that the other term is that ft d prime plus vt is greater than t hat. And this is exactly equal to e to the epsilon times probability that A prime is equal to the output A. So yeah, essentially we proved exactly what we wanted. You know, we started with probability that A is equal to A, and now we got to e to the epsilon times the same thing. So cool. That was a bit of work and it was a little bit technical, but you know, we managed to convert from one database to the other and show the statement we wanted. Now, it remains to reason about accuracy of this algorithm. How accurate is it? And what do we even mean by accuracy? Because the thing is, when we were outputting queries before, we were, you know, outputting a value. How much error do we have in terms of the numeric value of the query? But here, what we're doing is we're only outputting a top or bottom symbol, so it's not immediately obvious what the accuracy type guarantee is. Well, we want that our algorithm will make no mistakes with high probability. So we want to minimize the number of mistakes. What do we mean by mistakes? Well, we're going to say a mistake is when the algorithm says that a small query is larger than the threshold, or when a large query is smaller than the threshold. But since the answer to the queries are noisy, we're not going to be able to do this perfectly, so we're going to leave a little bit of slack. Specifically, we're going to say that we're going to let the algorithm is alpha beta accurate if the following holds. We want the following. We want for all I in the sort of range k, because there's k time steps total, we have the following simultaneously. You know, if we say that the algorithm outputs, if the algorithm outputs that you know, top, that means it's like a big query, then we have that fi on d is going to be at least greater than t minus alpha. So, you know, it's not greater necessarily than t, but it's greater than t with a little bit of slack. And then on the other hand, if the algorithm outputs bot, then we're given the guarantee that fi on d is less than or equal to t plus alpha. So you can see that it allows a little bit of slack in both directions for accuracy. And we want this, you know, this happens for all I with probability at least 1 minus beta. We have these types of guarantees. So yeah, the accuracy of the algorithm is kind of measured in terms of how big this alpha is, how much leeway do we have to allow it. And we have the following type of accuracy guarantee for sparse, for rather above threshold. So let's say where we have the following. There's k queries, and all but the last one are sort of significantly smaller than the threshold. So for all I strictly less than k, then we have that fi on d is going to be less than or equal to t minus alpha. So suppose this is our setup. Then we have that you know, above threshold is going to be alpha beta accurate for alpha equal to the following value: 8 log k plus log 2 over beta over epsilon. So in particular, it's not going to stop until the very final time. It's kind of something implied by this. But let's take a look at this accuracy guarantee, this theorem we have. So how much error do we have here? The amount of error we have is just scaling logarithmically in the number of queries k. So that's kind of what we were hoping for. When we started, we were saying we didn't want to pay polynomial, and so it seems like we're good. Yeah, the error guarantee is kind of comparable to what we would get if we did the exponential mechanism, but this has the added benefit of also being applicable in the online setting where they come at us one by one. So okay, here's the theorem, and you notice that, you know, the error probability, like with the accuracy decays fairly mildly with the error probability beta. Okay, so let's try to prove this. So the idea behind the proof is the following. Like, what we would ideally like to do is we would ideally like to compare fi of d with the true threshold t. But what instead we do is we compare fi on d plus this Laplace random variable here with the threshold plus some additional Laplace noise. So let me write the comparison we do. So we compare fi on d plus some new of I versus t, which is the true threshold plus the size of plus the random variable. Let's write it as, this is kind of a weird way of writing it, but I'll write it as the following just because it's based on the notation we set up. So in particular, this is the Laplace random variable. That is, I guess, Laplace, that's Laplace 4 over epsilon, and the other one is Laplace 2 over epsilon. And this overall thing here is going to be Laplace 2 over epsilon. Now, what I want to say is that, if we have here that the guarantee that all of them are kind of below the threshold significantly. And the idea is that if we were just comparing fi of d to t, then it would be less by a significant margin because it's less than alpha. But on the other hand, if we can say in fact that the size of nu I and the size of t hat minus t, if both these random variables are less than or equal to alpha over 2, then we have the desired accuracy guarantee. Why is that? So suppose if we had some ai which is equal to top, then this implies, based on this would imply that suppose we had this guarantee, that means that fi of d plus nu I is greater than or equal to t plus t hat minus t. So this is the guarantee we would have if it output at top. And rearranging this gives the following. It implies that fi on d is greater than or equal to t plus, I'm just moving this over to the other side. And this is going to be greater than or equal to t minus alpha over 2 minus alpha over 2, which is greater than or equal to t minus alpha. Remember, both of these are just because we're conditioning on the event that in fact their magnitudes are less than alpha over 2. And so this essentially gives us the accuracy guarantee that we wanted. We're saying, if it outputs this, then outputs ai equals t top, then we have that the query itself is greater than t minus alpha. So good, that's exactly the type of accuracy guarantee you want. And similarly, if you try to work it out for the other thing, then for the other case where it's where ai equals bot, you'll sort of see the similar type of thing. Maybe try working out to test your understanding. Okay, so all we need to do now to conclude the proof is show that, in fact, that these bounds hold with high probability. So we want to show this. So prove this. So this is not too hard to do. In particular, all we're going to use is the tail bound on Laplace random variables. And this can be derived just by looking at explicitly what the Laplace PDF looks like. So the probability that Laplace is greater than t times b is equal exactly actually to exp of minus t. And again, this just can be derived just by looking at the PDF of a Laplace random variable. But with this in hand, this can actually give us exactly what we wanted. Let's just do it for first of all, let's do it for the easier case, which is t hat minus t. So the probability that the magnitude of t hat minus t is greater than or equal to alpha over 2. Well, if you just sort of substitute this in and take the appropriate value of b, which is b is equal to 2 over epsilon, 2 over epsilon, because that's sort of how we define this difference here. Well, this will give us that this is equal to exp of minus epsilon alpha over 4. Similarly, we can do this for the other random variables. The difference is this time we have a set of this is not just one random variable. This is a set of k random variables. So we're going to also need to use a union bound. So what we're going to do here is we're going to argue about the probability that the max of these absolute values, nu of I, is greater than or equal to alpha over 2. And this we bound by k, because we're taking a union bound over all k things, times the probability that a single one is greater than this alpha over 2. So this is going to be exp of minus epsilon alpha over 8. And why is this 8 instead of 4? Well, the reason is because when we were defining these, we had a factor of 2 more in the parameter. So yeah, that's these are the two conditions. These are the probability that these two events happen. And so if you kind of invert these, what this tells you, like what we're going to do is we're going to set both of these events of failure to be less than or equal to beta over 2. Because these are the two ways that sort of the algorithm can fail based on, you know, what we showed above. And we set them each to fail with probability beta over 2 because the overall probability failure is going to be going to be beta. So just rearranging these we can see that these both will be satisfied as long as we have the following lower bound on alpha. In particular, you can just really focus on this one. You know, let's actually just do this one to be careful. So taking the log of both sides of this expression here, so that gives us log of k plus, or rather minus, epsilon alpha over 8 is less than or equal to log of beta over 2. And what we're going to do is, you know, rearrange this, move things to the appropriate sides. So this becomes log k, and we're going to move it to the other side, but also bring out a minus so that it flips it, plus log of 2 over beta is less than or equal to epsilon alpha over 8. And so this implies, for this to hold, we need that we have that alpha is greater than or equal to 8 log k plus log 2 over beta over epsilon. And recall, that's precisely what our accuracy guarantee was that we had here. And you can see that the same value of alpha will cause the other one to hold as well. So that essentially completes the proof that, you know, all we had to do was reason about how large the random variables could be and bound the probability that any of them is too large, which is very easy to do because Laplace random variables are rather conveniently bounded, or rather convenient to reason about. So that's it for the above threshold component, which just looks at a stream of queries and answers them one by one, whether they're greater or smaller than some threshold. What we're going to see in the next part is how to sort of chain this together in order to get the sparse vector technique, which can answer a sequence of these queries instead of just one.